our next question is, how can we tell if two variables are actually correlated? And we will do this by running a hypothesis test. So our hypothesis test has a null hypothesis where x and y are linearly uncorrelated. So if there is no correlation between the two variables, then that is an uninteresting result. And then our alternative is that x and y are going to be linearly correlated. And we're going to stick with the non-directional hypotheses here. Okay, so if x and y are linearly or uncorrelated, then that's where rho is 0. And then if x and y are linearly correlated, that's where rho is not equal to 0. So in this case, we won't consider alternatives where rho is positive and rho is negative. We'll stick with the non-directional test. Now, the test statistic for correlation has an interesting formula. It turns out to be the correlation coefficient R times the square root of n minus 2 over 1 minus r squared. And this is in fact a t statistic. It looks nothing like any of the t statistics that we have calculated before. And for now, I'm going to ask you to take this on faith that this is actually the correct test statistic. In a later video, I'll explain how this particular hypothesis test is related to and equivalent to another hypothesis test in which the test statistic will make more sense. And so for now, we're just going to take this on faith. The degrees of freedom for the t-test that we're going to do is n minus 2. And if you're thinking about like, why is this n minus 2? Well, any 2 points can define a line, and then there's no ambiguity about where the line is if you have 2 points. It's only when you have 3 points that you can introduce some ambiguity about where the line might be. And so the first 2 data points only just define a line. It's the subsequent data points, the ones that are the degrees of freedom, that will determine the best fit line. And as usual, we're going to reject the null hypothesis if the absolute value of our t statistic is bigger than t sub alpha over 2. So we're going to run a non-directional t-test like we have done before. So let me give you a couple examples. The first one is our global temperature versus CO2 concentration data, where previously we discovered that the correlation coefficient was in fact 0.963. And so the t statistic is equal to 0.963 times the square root of our degrees of freedom, which is 64. So that's our total 66 data points, minus 2. And then this is going to be 1 minus our correlation coefficient, 0.963 squared. Now, if we work that out, that's going to end up being 28.58. So our t statistic is very large. And so I don't even really need to look at the chart and the degrees of freedom or anything like that. I can tell you that this is going to be very significant and that the p-value is going to be less than 0.001, which is really an understatement. It'll be quite small. So here we see that there is a significant non-zero correlation between global change in temperature and CO2 concentration. Okay, so this is a very significant non-zero correlation. Now let's look at the SAT English versus GPA data, where the correlation coefficient was much smaller. So our t statistic in this case is going to be r, which is 0.353, times the square root, okay, of, in this case, our degrees of freedom is 343. And we're going to divide that by 1 minus 0.353 squared. Now, if we work that out, that's going to end up being 6.967. So this t-statistic is also quite large. A t-statistic of 6 is generally way off the chart. And so our p-value in this case is going to be 0.001, which means we have a very significant non-zero correlation. Now you may say to yourself, now wait a minute, the correlation is 0.353, which is not very close to 1. And so you would think this is a weak correlation, and it is a weak correlation. But the test that we're running to determine whether two variables are correlated is only testing to see whether correlation is 0 or not. And so what you have here is a weak correlation, but that weak correlation is significant in that it's not 0. And so you can see that this test is really not all that powerful. It'll tell you that the correlation is not 0, but it won't tell you how strong the correlation is. Okay, and it's important for us to be able to interpret like what it means to have a strong correlation. And so in a later video, we'll be able to interpret what this correlation coefficient is telling us in terms of the relationship between our two variables. Now I'd like to point out another thing about correlation, and that is the relationship with correlation and causation. So I'd like to show you a plot. Okay, so this is a plot of Nobel laureates per capita versus chocolate consumption per capita in various countries. Okay, and so what you can see is that there is a strong correlation of 0.791, and it's very highly significant. But yet, we have to ask ourselves, sure, there seems to be a relationship between chocolate consumption, Nobel laureates per capita and chocolate consumption per capita. Okay, but is that a causal relationship? Okay, does eating chocolate increase the chances of winning a Nobel Prize? And obviously that is not the case. What you have here is that you have a lot of European countries, right, with high chocolate consumption because they make a lot of chocolate in Europe, and it's very popular in Europe, okay? But then also, you can see the bias of the Nobel laureates in Europe, okay? A lot of European countries are dominating the Nobel Prizes. And so what you don't have is that chocolate consumption is causing an increase in Nobel laureates, but instead, possibly a European bias is causing an increase in Nobel laureates. And so I can answer my question, does eating chocolate increase the chances of winning Nobel Prize? And obviously the answer is no. Okay. There must be another explanatory variable. And if you look at the next video that's on my playlist, you can see some kind of fun correlations from a different YouTube channel.